This lesson is on section 3.5, polygons and their angles. The learning targets will be at the top of your notes. A polygon is a figure that is made up of segments that connect only at their endpoints. It doesn't matter whether it's 3 segments, 47 segments, as long as there's no curves, the segments only connect at their endpoints. That makes it a polygon. The way that you name a polygon is by the corners, which are called the vertices. You can go clockwise or counterclockwise around the figure, and it doesn't matter which one you start with. You just can't jump around. So if I started at D, I would say D, C, B, A, F, E, or D, E, F, A, B, C. I just wouldn't jump around. Polygons can be equilateral, which means they're equal sides. A rhombus is a good example of an equilateral polygon. A polygon can be equiangular, meaning it has equal angles. A rectangle would be a good example of an equiangular polygon. A regular polygon is a combination of the two. So that means it's both equal sides and equal angles. So a square or an equilateral triangle are good examples of regular polygons. A figure can be convex or concave. If your polygon is convex, that means that you can kind of draw a circle around it and it hits all the corners, all the vertices. You don't miss any. Whereas if your figure is concave, if I were to draw a circle around this figure, I would miss these 5 corners in the middle, these 5 vertices in the middle. They wouldn't be able to touch that circle that I drew around the outside. Another way to look at it is if the figure looks like it's caved in on one or more parts. That means it's concave. Okay, the corner, one or more of the corners is on the interior of the polygon. This chart shows the degrees of the angles that are inside and outside of a polygon. It also gives you your appropriate names for everything through a 12-sided figure. A 12-sided figure would be a dodecagon. Anything bigger than 12, and you just put the number of sides in for n. So for example, if it had 26 sides, it would be a 26gon. N stands for the number of sides. The total for the interior angles, so when you add up all the angles inside any of these figures, I give you the totals through 12 sides. For anything bigger than 12 sides, you're going to use this formula. This formula tells you what the total of your interior angles is. So I actually got these numbers by taking, if I was going to do a heptagon, I would do 7 minus 2, which is 5, and then 5 times 180. That's how I got 900. If I wanted to know what an individual angle is inside a polygon, if it was a regular polygon, then I could just take my total and divide it by how many sides I have. So if I took 900 divided by 7, that would give me what each one of these angles is if it's a regular polygon. If it's not, then all you know is that when you add them all up, you'll get 900. The exterior angles, the angles that go around the outside of a figure, notice that those are the same no matter what side, or no matter how many sides your polygon has. And that's because exterior angles go around the outside of a figure. So if you draw a circle around the outside of a figure, a circle's 360 degrees. So to go around an outside of a figure, you're going to make a circle and it's going to always be 360 degrees no matter what. Okay, so let's look at some examples. We're going to use that chart on the last page to help us with these examples. So what is the measure of the total of the interior angles of a pentagon? Okay, nope, this should say, oh, sorry, this should say interior, and this should say exterior. I forgot to change those, sorry. If we go back, so the interior angles of a pentagon. So I go to pentagon, interior angles, the total would be 540. If I didn't know that, I would use that formula down at the bottom and I would say 5 minus 2 and I'd get 3, and I'd take that times 180. Either way, I get 540 degrees for the total. And then if I want to know what each interior angle is, since if it's a regular polygon, I would divide it by how many sides it has. So I'd divide by 5, and each angle would be 108. If it's talking about exterior angles, those are a little bit easier because it doesn't matter how many sides it has. We know that the total of the exterior angles is always going to be 360. But if I want to know what each exterior angle is, if it's a regular decagon meaning it has 10 sides, I would divide by 10, and each exterior angle would be 36 degrees. Now what's interesting is that exterior angles and interior angles of a polygon have to add up to 180 degrees, because if you look at, if this is the interior and this is the exterior angle of any polygon, they make a straight line. So they're going to add up to 180 degrees. So I can use the exterior angle. If the exterior angle is 36, I can find what the interior angle would be, because I can just take 180 minus 136 and I would get 144. So the interior angle would be 144. So you can go back and forth between interior and exterior angles. If you know one, you can find the other. All right, let's look at this one. If the total of the interior angles is 900, how many sides does it have? Well, one of your options is obviously to go back and look at the chart and say, hey, 900, total of the interior angles. I know it's a heptagon. That's the easiest way to do it. Another way to do it is to use that formula and leave n in for your number of sides because you don't know it, and know that n minus 2, that's not a very good 2, n minus 2 times 180 has to equal 900. So you would divide by 180 and then add 2 to get back to n. And if you do that, when you divide by 180 and then add 2 to get the n alone, you end up with 7. Either way. Another example, so if I need to find a missing angle measure, I have to know how many sides it has because I have to know what the total would be. Okay, so I count my number of sides. This happens to be 5 sides or a pentagon. So I know that my total from my chart says that the interior angles have to add up to 540 degrees. So I would take 540 and I would subtract off the 99, the 106, the 81, and the 151. I'd subtract those all off. And then whatever's left, which in this case is 103, 103 would have to be this angle measure. This angle would have to be 103. Okay. Sorry, my writing's not very good right now. Number 5, if I just want to name a polygon and then classify it as convex or concave, again, I have to count up my sides. So 1, 2, 3, 4, 5, 6, 7. It's a 7-sided figure. So then I know that that's a heptagon. That's on my chart that I can look at. And then convex or concave, if I draw a circle around it, am I going to be able to hit all the corners? And the answer would be no. I would miss this one. See how it's caved in right here? So that means it's a concave heptagon. These, again, deal with our chart. So if I know that each of my exterior angles of some polygon is 10 degrees. So I have some random polygon and I know that my exterior angles are 10 degrees. How can I figure out how many sides it has? Well, the good news is if you have an exterior angle, you know that the total of your exterior angles is going to be 360. So if I just take 360 divided by 10, that tells me I'm going to have 36 exterior angles, which tells me I'm going to have a 36-sided figure, or a 36gon. Okay. The total of my exterior angles, no matter how many sides, we know is 360. But then to get to my interior angle, I'm going to use that concept of supplementary. I'm going to use my concept that these angles add up to 180. So if my exterior angle is 10, my interior angle has to be whatever's left to get to 180. So my interior angles would be 170 degrees. Another example, but what if I start with the interior angles? I have some polygon, I don't know how many sides it has, but I know that my interior angles are 167 degrees. Okay? We don't know what the total of the interior angles are, but I do know that if my interior angle is 167, that my exterior angle would have to be whatever's left to get to 180. So I would say, my exterior angle has to be 13 degrees. Now I can do it just the same way as I did this one, because I know my exterior angles have to add up to 360. But when I divide 360 by 13, I don't get a whole number. I get a decimal. I get 27.7. Well, when you look at a polygon, if it's a regular polygon, it can't have 0.7 of a side. So if this is what happens, if you take 360 divided by your exterior angles and you get a decimal, you can't have 27.7 sides of a regular polygon. So if you get a decimal here, then this polygon does not exist. Okay? If I would have gotten a whole number, let's say it would have been 168, and that would have made my exterior angle 12. When I take 360 divided by 12, now I get a whole number, and then I know how many sides my polygon has. But in this case, since I got a decimal, I would say that this one doesn't exist. Okay? That ends this lesson.